Hello everyone, and today I would like to discuss about interactions between particles that compose of the matter, how those interactions or how the strengths of those interactions will determine the macroscopically observable properties, or we call them material properties, or sometimes referred to as material parameters, such as the melting point and the boiling point. So let's review the concept learned so far. The key one will be the kinetic molecular you learned in the previous section. The one key point for that is when for all the matters is composed of particles. Those particles are in constant motion, and to which the extent of the motion will determine the states of matter. And we're going to refer to the classic one. There will be solid, you will be liquid, and you will be gas. And how actually those kind of the mental picture, the modeling you're going to have. Right now we're going to take a quick detour, go to a simulation program, and revisit this topic. Let's switch back to the University of Colorado produced a very nice JavaScript-based simulation, and in this case it's a state of matter. What you're looking at here is neon. It has a 13K. In this case, the temperature is used. It's called the absolute temperature. The unit is Kelvin, not commonly used Celsius or Fahrenheit. And the Kelvin, the relationship between the Kelvin and the Celsius is you take the Celsius. Take the temperature in Celsius degree, you plus 273, then you will get Kelvin. So 13K is minus 260 degrees Celsius. At this temperature, neon atoms kind of still move, vibrates, but they vibrate very, very little. They cannot get past to each other. So now you're looking at this is a very nice model representing solids. We have the particles, in this case neon atoms, vibrating to a much less extent, so they do not pass each other. But as you know it, especially when we start turning down the heat, as you can see, the particles, in this case neon atoms, they start to vibrate. They vibrate more and more and more. And at certain temperatures, in this case it's 28 Kelvin, now you can see them pass each other. And it cannot hold the shape anymore, so it starts to spread. However, they cannot get too far away from each other, even though some of them did get farther away, but they kind of always fall back. So this is actually the neon is in its liquid state. And you keep on putting in the heat. As you can see, at about 37, they really starts to vibrate more and more and get far away from each other as the temperature further increases. And you will see a typical representation for gases. See, all those particles are moved very fast, randomly passing each other, and they collide with each other. However, there is no long-range order, and now it is all over the place. In this case, this is the gas. Gas is going to fill the container completely. So then let's take a look at the kind of different pure substance oxygen, and you can see the oxygen is 194K. It is in this gas. It's in this gas phase. And you can see them bumping into each other, but they are far apart. As you start taking the heat off, as you start taking the heat off, which means in essence reduce the temperature, slow it down, and it starts to agglomerate. Okay, it starts to really agglomerate as the temperature kept on going down. So now they starts to assemble into what we call the lattice structure. And it's not, showing very well here, but still you can see it starts to vibrate, but now they cannot, still get too much bypass each other. So this is about, is it between the liquid and the solid. It will take further reducing temperature, and in this case, so now you can see it's 33K. Now you can see the oxygen molecules, they cannot pass each other anymore. They vibrate, they still vibrate. So this is actually a solid oxygen. But now you're looking at the temperature, it's very, very low. Take a look at the water. Very interestingly, and this we're going to see this is the solid water. This is the solid water, and if you want to see it's 157 K, well below 0 degrees Celsius. And now start looking at at temperature. The water is liquid. Water is a liquid. This is a very good representation of liquid water. You can see them pass each other, but not too far away. And now I see the gas is 809 K. It's 809 Kelvin. So then now it really starts to move. And this is the picture for the gases. The picture for the gases. Okay. So you can actually pause, take a kind of snapshot. You can actually forward in a step fashion. Very, very useful simulation program. Very, very useful simulation program. So then what we learned from there is the transition between states of matter, what we call phase transitions. There are characteristic temperatures associated with those transitions. So this is where the melting points and the boiling points are coming from. So those are the temperature indication for the onset of a phase transition. So then let's examine in some real world some cases about the different kind of compounds. For sand, this is methylated silicon dioxide, and this one will be the SiO2, silicon dioxide, and that will give you about 1723 degrees C. Then you put in the magnesium fluoride, okay, so it's 1261, it's more than 1,000. And if you have the salt, table salt, if we're talking about sodium chloride, the melting point, this is what we talk about, the melting point will be 801 degree. And table sugar, you'll have the melting point for about 146. And everybody knows for water, the melting point 0 degree Celsius. Nitrogen, and this case is nitrogen gas, and nitrogen gas will be N2 minus 209.86 degrees. And benzene, and the melting point is 5.5 degree. And butane, you know what it is from the previous section, and it's minus 38 degrees C. As you can see, those numbers are all over the place, Then you start asking the question, how come those melting points are really, really different from each other? So then, in order to answer that, you have to go back to the kinetic molecular theory. You have to look at it, the process of melting. That is what's associated with the melting point. The process of melting is essentially make put in more and more thermal energy and make the particles vibrate more and more so they can pass each other. So then what is actually, so the key question here, the key question is here, what is holding? What is holding those particles that compose the matter together? And in this case, if it's a solid, what is holding those particles together? It's actually, should be the interactions between the particles, sometimes referred to as forces between those particles. Okay, so then the logic extension would be, the logic extension would be let's redo it. Stronger interactions between the particles, higher melting points and boiling points. It kind of makes sense. So essentially is the temperature, the thermal energy has to be taken in to overcome the attractions between those particles in order for them to start to move more, to go from the solid to liquid. So that you can see here, and you probably would start thinking about silicon dioxide has a very strong the forces holding them together. The ionic compound, magnesium fluoride, is pretty good, it's more than 1,000. The salt is sodium chloride, we covered in the in previous unit. So then this is actually 800. It's pretty significant. And sugar is kind of intermediate, but it starts dramatically decrease. Water has 0, and you can look at the nitrogen gas is minus 210. Benzene is about 5.5, and butane is minus 130. So you can see, now you can start seeing, predicting the interactions between the particles. The interactions between the particles. So now let's take a look at what kind of interactions between those particles. The first we're looking at is compound like a sodium chloride. As you learned in the previous unit, is actually those are composed of ions. So the ions of sodium is plus, chloride is minus. As you learned in the previous unit, they actually have a solid form. They actually have this alternating repeating pattern. Okay, so in this case it would be minus, plus, minus, plus, minus, plus, minus, plus. So there will be plus, minus, and they go on and on practically forever. So then you can actually have a cube full of those ions. Okay, so those are called ionic compounds. So now the key interaction will be the plus and the minus. this is very strong attraction. And this is based on electrostatic interactions between ions. So you would expect this to be very strong. So then what you expect to be the melting point, the boiling point for the ionic compound, high. So those would have high melting points and boiling points. The second type we're going to look at it will be metals. As you can see, for the metallic bonds, we can have the in this case metal cations. However, now you have free moving valence electrons. Okay, so those are the metal. This is the model for the metal, and remember, those are negatively charged. Still, you have negatively charged electrons interact with positively charged metallic cations. So it's still positive negative interaction, very strong. Just for the reason it's still positive negative. So you would think for metals you will get very high melting points and boiling points. Okay, so those are the ones with the very high melting temperature and boiling melting point and boiling point. So the third one we talked about in the previous section 2 is, well, there's not exactly ions exist in this pure substance, and it's not metal, so we're not talking about a metallic bond. In those type of pure substances, those are half molecules, so are molecular compounds. Okay, so those are molecular compounds. Essentially, you can represent it by molecules. As you can see, you can easily draw it representing them. So what is actually holding this together will be determined by the interactions between the molecules. So those right dots are the interactions between molecules. Those red ones is what we call it intermolecular forces. Those are responsible for holding the matter together. Okay, so this is called about intermolecular, meaning between the molecules. However, I have to specify, really emphasize on what we talk about is between molecules. It's not within the molecule. Those are intramolecular intermolecular forces, generally in the form of covalent bonds. Because of the nature of the covalent bonds covered in the previous units, it's still positive and negative. So the intramolecular forces very strong, just on par with the ionic. As we talked about before, the ionic bond strength actually is pretty much on an equal footing as for the covalent bond, the ones holding the molecule together. However, this has nothing to do with the melting points and the boiling point, because those ones, the intermolecular forces will determine that. The intermolecular forces will determine that. And let's take a quick look at kind of application examples. All right. So I'm going to give you a list of compounds with their formulas or formula units, and then your task is to kind of separate them into two groups. One group with fairly high melting points and boiling points. The other group with fairly low melting points and boiling points. So here comes the formula or formula units. CaCl2, Ti, CH4, and Fe, FeCl3, and H2S, He, and the nitrogen gas. So how do you approach this kind of problems? And you just learned what is actually holding them together and what determines the magnitude or the position or the location of the melting point or the boiling point. They're determined by the interaction between the particles. And then the ionic and covalent, the ionic and the metallic, those are the strong ones because it's positive and negative interactions. And only when we got to the molecular compounds, the intermolecular forces, but intermolecular forces are much weaker than the chemical bonds. So in this case, if we can identify the ionic compound and metals, separate them into a high melting point or boiling point group, the rest, the molecular compounds, will go into the low end of the melting points and the boiling points. As you can see, this is ionic compound, this is ionic compound, this is a metal, and that is a metal. Don't forget, titanium is a transition metal. Okay, so the one with high melting point would be calcium chloride because it's ionic compound, metal, titanium, metal, iron, and iron 3 chloride. The one with the low melting point will be CH4, and you know it's molecular compounds, H2S, molecular compounds, elements, monatomic elements, diatomic elements. So those are the ones you can separate them quickly just by looking at there's three big groups of interactions that hold those matters together. Hence, will determine the melting points for those substances. And you can see the ionic compound and the metallic, the metals, generally has very high melting points and boiling points, if those boiling points are accessible. And then contrast that with molecular compounds. Molecular compounds tend to have a very much weaker intermolecular forces that holds them together, so much lower melting point. So then let's take a little bit closer look at what we call it intermolecular forces. Mainly intermolecular forces would cover the molecular compounds. Okay. As you know it, in the molecular compounds, there's no permanently separated ions, so we only have molecules. But then in the previous unit, we also have this assessments to look at the overall distribution of the electrons, essentially the valence electrons surrounding the whole molecule. If you have an uneven distribution of that, and you have polarity. And we're just going to do a quick review on polarity. Okay, the concept of polarity. This is essentially the measure of how evenly the electrons are distributed. If the distribution is even, that will be nonpolar. If the distribution is uneven, that will be polar. Okay, this is polar, and later on we're going to say it has actually dipole-dipole moments. Take a look at some molecules. That's very simple ones. Remember, the hydrogen and the hydrogen atom form a hydrogen molecule by sharing one of their valence electrons. So by sharing this, you have two valence electrons for each of those atoms, happy helium electron configuration. And now notice the location of the shared valence electrons is right in the middle. There's no preference for the hydrogen on the right or preference for the hydrogen on the left, because they're identical. They have the identical pole on this pair of electrons. As a consequence, those two electrons probably on average will spend half of the time on hydrogen, half of the time on this right hydrogen, then half of the time on the left hydrogen. So you end up with even distribution. Okay, so the distribution is even, so the whole molecule is nonpolar. It's essentially cancel each other out. Well, however, if you're looking at HCl, hydrogen chloride, it also will share a pair of valence electrons. However, this time the way it is sharing, the pair of electrons is much closer to chlorine, as you know it, because chlorine has higher electronegativity than hydrogen. Since this pair of electrons spend more time, more than 50% of the time on the chlorine, it will cause chlorine carry a slightly negative charge. Since the hydrogen is losing that, so then it actually carries slightly positive. This is slightly negative, this is slightly positive charge. And now you have a permanent dipole as indicated by this arrow, and in this case its distribution is uneven and the molecule becomes polar. Okay, I want you to relate polarity, the polar of the molecule, with the overall distribution of valence electrons. Polar is uneven. You have dipole moments. What we call this is, change the color, it's called dipole moment. Okay, so this is a dipole moment. If I really want to reproduce the HCl, I have to, inform people about the relative distribution of electron density. You have more on the chlorine, less on the hydrogen. So it's slightly positive, slightly negative. The reason I use the symbol delta, small letter delta, is because even though the chlorine has the stronger attraction for the valence electrons, but it's not totally grabbed. So this valence electron still being shared between the hydrogen and the chlorine. So it's not a complete separation as in an ionic compound. And also, more importantly, you have, this is what we talk, sort of the individual chemical bond polarity. First, we have to have individual chemical bond polarity before you can actually get to the polarity for the whole molecule. So polarity for the whole molecule, that is molecular polarity. So this is, you have to add individual polar bonds. In 3D. Okay, so don't forget that. And the case in point will be water. So if we have water molecules, will be drawn like this, with about 104.5 degrees between them. And now you'll have individual polar bonds. You can add up to an overall overall dipole for the molecule. If I really want to represent water, on the oxygen side will be slightly negative because it's higher electronegativity. On the hydrogen side, slightly positive. So now we're looking at the polar molecules. Here's a good representation about water molecule. As you can see, you have the hydrogen and you have the big oxygen. And oxygen by default, this is actually a tetrahedral shape for the electron group geometry. Take the two pairs of lone pair, we call the lone pairs of valence electrons. Then you have this band shape because it's part of the tetrahedral. And now you have on this red represent oxygen has slightly negative, the other one has slightly positive. So now you actually have a situation, you will have a molecule, those are positive, negative, and you can see I can be positive, negative, this one will be positive, negative, but now it gives you the ability to start interacting favorably. You can have, that's an ugly drawing, I want to kind of get rid of that. Okay, get rid of that, bring it back. So then you would have positive, negative, positive, negative, positive, negative, negative, positive, negative, positive, negative, positive, as you can go on and on. So now those regions, partial charged regions, starts to interact. So those interaction, it's providing the intermolecular forces that holds molecules together. As indicated here for water molecule. So those are the ones, what we call it, this type of interaction, we call it dipole interaction. Essentially, this is polar molecule. This is essentially also the let's erase this. Let's rephrase this. This is essentially the positive and the negative interaction. But here we do not have a complete separation of charges. So those are only partial charges. So you would anticipate those interactions will be much weaker compared to the ionic or metallic bonds when they hold the material together. So now you start seeing, oh, interestingly, if the molecule is polar, this polar dipole-dipole interaction is available to enhance its ability to hold the material together. Okay, but you quickly would think, wait a second, we have some molecular compounds that lack overall polarity. How to do then? Where is the determining factor that is holding this material together? In the solid state or in the liquid state? In the solid state and the liquid state. And this is actually coming down to something that is kind of difficult, a little bit on the difficult side to understand. So then, when they only have the blobs, what will be the interaction between them? So this is actually going to be summarized as what we call the London dispersion forces in this case. And as you know, any material is composed of atoms or the ions. Atoms have electrons moving around them. So as a nonpolar molecule means on average extended period of time, the average is nonpolar. There's even distribution of valence electrons over time. Same here, it will be the even distribution. However, at any moment, because of electrons are moving, because of electrons moving fast, so any snapshot, you will have slightly more electrons on this side, less electrons on that side. Okay, so then it will be more electrons on this side, on that side. On the other side, you will have this minus, more electron, and the plus. So now you start having interaction of those, what we call it, instantaneous dipoles, or sometimes referred to as induced dipoles. So those are the ones, sometimes it's called instantaneous. Okay, so some call it instantaneous dipoles. Because this is just because of the uneven distribution snapshot, just at any given moment, because of the movement of those electrons, you will have those instantaneous dipoles. But at the other time interval, and this will be reversed. So then this one probably will have the pluses and the minuses. So overall, on average, on timed average, it's no net polarity. But at any given moment, you would have this arrangement that will give you the interaction between partially charged particles. So this is the instantaneous dipoles, and that determine the melting points and boiling points of substances. As you can see, the London dispersion force is much weaker. So this is actually the weakest interactions. So now you understand the distinction between those two. Let's do some exercise. Okay, remember, let's recap. So the ionic is, or metallic, much stronger interaction, hence highest. Metallic has highest melting point, and then it will be followed by the dipole. Dipole. If the molecule has permanent polarity, you have permanent dipole. So the dipole-dipole interaction will be followed by that, and this will be followed by London dispersion forces. Okay. Interestingly, these two are combined with a terminology called van der Waals. Van der Waals. This is van der Waals forces. This is a relative ranking too. Okay, this is a relative ranking too. So then, let's pause. So, and here is a schematic illustration about the London dispersion forces. The one of the key characteristics of London dispersion forces is, as you can see, when you have more electrons overall within the molecule, the more instantaneous dipoles you will have, because it has much higher propensity to have this spontaneous uneven distribution of electrons. The more electrons to move around, the more instantaneous dipoles you will have, stronger interaction will have. So more electrons, relatively stronger London dispersion forces. So what do you mean? More electrons generally means higher mass. And shown here, in this case, we have all CH4, CF4, CCl4, CBr4, and CI4. All of them, as you go through the process, you will have a tetrahedral shape because all the bonds are identical, so you have net zero polarity for the molecule. So in this case, as you can see, no ions, no metals, and no permanent dipoles. The only interaction you're going to have here is London dispersion forces. As we as we said before, London dispersion forces scales with the mass, how much you have it here. And now you say you have a CH4 as the lowest one and the CI4 has the highest one. You can see the melting point. It's trending nicely. It's trending nicely. Go from the negative, almost it's lower than negative 180 to about 170. And the only thing changed here is the mass of the compound, because all of them don't have any permanent dipoles or molecular polarity. So this is a nice illustration of that. This is a nice illustration of that. So let's do some little exercise. Let's do a little exercise and to see how much you understand that. And let's see examples. A pair of compounds, carbon dioxide versus sulfur dioxide. Which one has a higher melting point? Okay, so which one has a higher melting point? As you can see, for the carbon dioxide, go through the process, the steps, Lewis structure, ABXY notation, and then you go to this how many electron groups you have to take care of, and in this case it's 2, so CO2 is linear and consequently nonpolar. Okay, so the SO2 is a different story. If you go through that, and the shape will be bent, due to the pair of electrons left on the sulfur central atom. So this one is actually bent and is polar. So as a consequence, the SO2 will have higher melting point. If you check on the data, the melting point for SO2 will be minus 72 degree, for CO2 minus 78 degree. Take a look at another comparison. CH4 versus PH3. And as you can see here, go through the process, and this one will be tetrahedral in shape and nonpolar. Okay, so this one will be molecular shape, will be trigonal pyramid. Okay, so this one will be trigonal pyramid, but slightly polar or near nonpolar. Okay, but then have the one, this one will be 132.8 degree, and CH4 will have negative 182 degree. Okay, so with that, we need to cover the last special intermolecular forces. We're going to call it the hydrogen bomb. And this is going to be covered in a separate broadcast. With that, and here's the end for this particular broadcast. Thank you very much for your attention.